So first, a little bit about myself. My name is Artem, and I am a principal security engineer at Trail of Bits, a small New York-based computer security startup with lots of remote employees, of which I am one. And at Trail of Bits, I was our primary investigator for DARPA's Cyber Grand Challenge, which means that I was the one in charge of building our automated bug finding and patching system. So this talk is going to have several themes. The big overarching theme is going to be how Trail of Bits fared in the Cyber Grand Challenges and the ups and downs that we faced throughout the process. Essentially, it'll be a story of a small group of ragtag computer security researchers starting in nothing and creating a pretty kick-ass bug finding system. We're also going to talk about new approaches to bug finding and how some of the ways in which we are building our automated bug finding tools is fundamentally wrong and won't scale, and what we should do to be different. And also, there's going to be some side discussions about distributed systems, DevOps, and automated patching. So every story has a good beginning, and I was working at a different job with Andrew, one of the guys from Trail of Bits, on a different project, and he comes up to me one day and he's like, "Hey Artem, how about you go work at Trail of Bits and lead our CGC team?" And I was kind of skeptical about this since I never really led a team before, especially a remote team, and I wasn't really sure if I was ready for the responsibility. But Andrew could be very, very persuasive, and so we decided that we should go for it. And so on I went to begin the story. So I've been mentioning CGC and Cyber Grand Challenge a lot. And I know Dave just gave a brief introduction, but I feel I should explain a little bit more for those of you who are unfamiliar. So first of all, CGC is one of DARPA's grand challenges, which is the thing like the self-driving car challenge or like the finding the red balloons challenge. And this means that it's a competition. So lots of people compete, but only the top 3 or so win money, and everybody else gets nothing. And this competition was to hold a capture the flag style contests between machines with the goal of automating bug finding and patching in binary software. And like these weren't like simple 3-line binaries. These were like legit programs specifically created for this challenge that exhibited like real bugs like use after freeze and heap overflows and custom format string vulnerabilities. And also, the goal was to find bugs in binary only software. So we were not provided with any source code. It doesn't have to work in binaries. And as you can tell, this would be kind of hard, which is why it was a DARPA project. The only simplification that we got was that everything was for a simplified Linux-based operating system called Decree, which is Linux-based but only has 7 system calls. So all the competitors could focus on the actual tasks of, like finding and patching bugs instead of dealing with like Linux system call complexity issues. And so with any competition, there's a way to win, and this is how scoring was done. So scoring had 3 components. First, you gain points for patching bugs in binaries. And you have to patch some bugs to score. There's no way of getting around it. That was one of the base rules. And also, you gain points in CGC for finding bugs. However, your bug finding score only counts if you also patch that bug. And you added up these 2 scores from bug finding and patching, and then you scaled it by the performance of your patched binaries. And so I don't expect you to be able to fully read this graph here. You just need to see that there's like a big sloping downward line that goes down really quickly. And that's to show you that the performance penalties are super linear, which means that, for instance, if your binary runs 3 times as slow as the original, you're not going to get 1/3 of the score. You're going to get much less. You're going to get like 1/10 of the score. Also, in any competition, there's competitors. And there were about 200 total people registered for the Cyber Grand Challenge, but the 800-pound gorilla in the room was 4All Secure, which was an offshoot of Carnegie Mellon University. And you may remember these guys from this paper, which is Mayhem. Mayhem was a paper describing how to build a system to find bugs in binary code in 2012. And so these guys already had like a 2 to 3 year head start on everybody, and they were in this thing. And so we were not about to let this discourage us. We weren't going to enter this just to do okay or just to qualify. We were going to go in this and we were going to win. And so our goal became, how do we build a system that can win CGC knowing the kind of competition that we faced? And our solution to this, and it's codenamed Cyberdyne. And it's named Cyberdyne for the evil corporation, the Terminator franchise, that creates the artificial intelligence that destroys all of humanity. And so, step one in building an automated bug finding system was to get help, because you can't do this alone. And so we had a fully distributed international team. We had people from 4 different cities, from 3 countries and 3 time zones. In case you guys don't know the flags, it's Canada, Argentina, and the United States. And interestingly enough, we worked completely remote, and we actually had never all met physically in the same spot until well after our part of the Cyber Grand Challenge was over. But having people to develop isn't enough. Sometimes you run into certain situations where you just need some kind of magic or wizardry to get you out of where you are. And so we also needed to get some wizards. And I don't know if you guys are familiar with these 2 people. The person on the left is Andrew Roof, who's a PhD student at the Programming Languages Group at the University of Maryland. And the guy on the right is Alex Sadarov, who's the co-founder and CTO of Trail of Bits, and also currently taking the NOP certification. So we had our wizards, we had our development team, and then we needed to figure out, like, what do we build? And so we did some back-of-the-envelope calculations, and like, okay, DARPA promised us there's going to be at least 100 binaries. You know, we have 1 core for finding bugs, 1 core for patching them, so it's like, what, 200 cores maybe? Like, this isn't going to fit in a single box. So you're going to need to build a distributed system. But to distribute something, like, you need to know what you're distributing. You can't just, like, distribute nothing. So you also needed to build, like, the bug finding and the patching pieces. And so we had this chicken and the egg problem. Did we build a distributed system first, or did we do the bug finding and the patching first? And I chose that we should build the distributed system first, which was, we'll see, ended up being a terrible, terrible mistake. But I had a really good reason for this, and that's because the idea was we should get this part out of the way so it works, and then we can focus on building like a really great bug finding and patching thing and just watch our score rise. And so our ragtag adventure's first quest was to learn DevOps. And so we needed to learn DevOps, well, because this is a picture of the Trail of Bits New York office, and this is the biggest office we have. And as you can see, there's not really a lot of room to put like a server rack and like cooling and the power requirements for it. Not to mention, there's not really room for an IT guy to manage all this stuff. So for those who don't know, DevOps means treating infrastructure as code. And so we were going to need to do some cloud-based DevOps. And so why DevOps? Well, it had several appealing principles other than the fact that we didn't have the space for like hardware. One of these was that one of the core tenets of DevOps is that you automate everything. And we had like a hard time limit, and we had very few people resources. So the more stuff you could automate, it meant the less stuff you spent doing useless IT work, and the more time you spend like finding and patching bugs. The other part was that DevOps is going to be repeatable because everything is scripted and automated. So there's not going to be that thing where like you have a magical build of the system working on your laptop and like you have to transfer it to the cluster that does the work the night of and you're panicking because something won't link. Like that's supposed to go away. So there's no more works on my machine. And finally, the most important reason we wanted to do DevOps was a fast build, test, debug cycle. And this was essential since we wanted to get the IT done and out of the way so we could just focus on building the tools and watching our score graph rise from, bottom left to top right. With any DevOps presentation, you need a technology stack slide. So this is the first out of our 2 technology stack slides. And we went full hipster. So I don't know if you guys are familiar with all of these things. So Docker is used for containerization and isolation of microservices. And we were like, yeah, we totally need this. Like we have all these services that are communicating with each other. If you isolate them, we can test them individually, and we can, try out new versions of things without disrupting everything else, and like this is going to be awesome. And so etcd is used for making all of these services like bootstrap with some configuration and share metadata. And you're like, well, you have these services, we're going to need to have them share metadata and work together. So we're going to need that too. And React is a distributed data store. And you're like, well, we're going to have to store a lot of stuff. You have this distributed thing, you might as well have a distributed data store. And finally, Elasticsearch, Logstash, and Kibana is known as the ELK stack, which is going to do distributed logging and like pool log analysis. And we're like, yeah, we can just pipe the logs there, and we can generate our graphs by analyzing the logs. And so we were super excited to go into this, and then we found out that everything is terrible. So anybody who tells me that distributed solutions to your problem is lying, they're probably wrong. Docker was the worst one of these. Like I could spend a whole hour talking about the things wrong with it, but even though the idea is fantastic, the implementation is awful and full of bugs. For one thing, every single disk storage backend for Docker is broken. All of them, but just in different ways. You just have to find whichever one you like that has the bugs you can deal with. etcd will start giving you wrong results for metadata reads under high load. React is slow, and it's based on Erlang, and the Erlang standard library couldn't handle 3-digit CPU loads, so then it would crash when the box was really loaded and then restart itself, and that was not fun. And ELK stack was the worst of them all because, so we got the latest version from the elastic.co site, but it turns out they were shipping one with like a 5-month-old ODE in it, a Java deserialization ODE, by the way. And it would have been fine had Docker not silently disabled your firewall rules, unless you give it a special flag saying, do not disable my firewall rules. And so we ended up actually getting owned by some random internet guy scanning for this known vulnerability, despite the fact that we thought we were double protected from it. Yeah, not a good time. So this is the second part of our DevOps technology stack, and these are just things that are good, or at least okay. So Ansible is used for automation of provisioning via SSH, and this is fine as long as you stick to a certain version of it and don't change anything else, because as soon as you upgrade version, it'll break all of your scripts. Redis or Redis, or however it's pronounced, is it does in-memory storage, and it's also a pub sub system, and it's absolutely amazing. It just doesn't fall over, and it works, and no matter what we threw at it, and no matter what load and what capacity, it just did its job. I'm really happy with it. The best one, though, is Amazon Web Services, and I'll have a lot more good things to say about them later in another part of the presentation. But they have tech support that will actually help you. So, one of the things we had was we had a problem with Docker again, using one of the disk backends, causing our boxes to freeze, and we were like, our EC2 instances are dying in the middle of our runs, and we don't know. And so the Amazon guys actually looked to our kernel trace logs, and they were like, this is your problem, you're using Docker with this disk backend. Here's upgrade to this other random kernel point provision, it'll fix it. And it did. So yeah, it costs more to run AWS and other cloud services, but it's totally worth it. And so, after several months, we had progress. So I don't expect you guys to be able to read all the details of the slide, but this is one of the actual system diagrams. And we had stuff here that was just the green boxes were distributed, and the arrows show up how they were communicating, and this stuff was working. We had some kind of distributed system that talked to each other and did things, and that was pretty cool. We were excited. And so the challenge had 2 test runs. So it was a year of work from the announcement of the program to the qualifier event. And in between, there were 2 test runs, so you could test how your code works with all of DARPA's stuff, make sure that your system is working, and everything is in order. And so the first one of these was about 6 months through in December of 2014. And so we got our stuff ready for the trial run, we got their binaries, and we ran it, and we scored 0. You didn't get any points at all. And so it turns out that most of the time we'd actually spent trying to get the system up and running. Because even though we thought we had everything working, it wasn't as simple. When we went to distribute it in EC2, there were all kinds of problems. And eventually we got this thing running, but barely enough time for it to actually do anything. And so it was wow, we spent 6 months and we're still scoring 0. And so I go to our wizards, and I'm like, guys, we're in trouble. We've spent a lot of time and we haven't really made any progress. And so they offered me some very insightful advice, which is have you tried scoring points instead of spending all this time building this distributed system? Maybe go and find some bugs. And I was like, yeah, that is a really good idea. We should do that. So our team's next quest was to go and find some bugs. And so it's going to be kind of tough, since a lot of the time had already been gone, and we still haven't really gotten anywhere. And so I wanted to find what a bug is, since a lot of people say, oh, bugs, there's lots of things that are bugs. So for this case, bugs is specifically defined as memory safety violations. So some kind of unbounded memory access, either unbounded spatially or unbounded temporally. And there's lots of things that weren't considered bugs for this that could have been bugs, such as like authentication bypasses or race conditions. So like we're not looking for those. So anytime from now on you hear me say bug, think memory safety violation. And so as I said, we needed some wizards, which luckily we had plenty of. And we were like, guys, like, we need to figure something out. Like, we need to find some bugs in a hurry, and we need to match kind of the performance of what Mayhem did. And like, they had 6 more months to fix their stuff, so we really need something good. Let's pull some rabbits out of the hat. And we found it. So I'm going to describe how we find bugs. And to do that, we're going to do a little quick dive into bug finding theory. So bug finding theory 101. There's no analysis you can have that you can run in a program that will find you all the bugs and just the bugs. It's provably impossible. You're going to run into the halting problem. You just can't do it. So you end up with 2 main alternatives. The first alternative is you can over-approximate how many bugs are in the program. And so over-approximate analyses will find you potentially all of the bugs that do exist, but they will also find a lot of bugs that don't exist. It'll have false positives. It'll say things that are bugs that are not. And sometimes this is okay. This may be what you want. So for instance, this is used in things like points to analysis or alias analysis and compilers. Like all of those things over-approximate. And the other side of this is that you can also do under-approximation. And so under-approximation isn't guaranteed to find you anything at all. It could find you nothing. But the stuff that under-approximate analyses will find you is guaranteed to be legitimate. And typically, under-approximate analysis works by sampling actual executions of the program with some kind of input. And like pretty much like all the tools that you're going to find that are actually used to secure production code are in the category of under-approximate analyses. So, as I said before, under-approximate analyses aren't guaranteed to find you anything. And typically, each under-approximate analysis has things like roadblocks. And a roadblock is something in the code that stops the analysis from moving forward. So for instance, in this example, where you're comparing an input to a random 32-bit decoder, that's just like a header check. So for instance, for a naive brute force fuzzer, this is going to be really, really hard. It's going to have to do like 2 to the 32 tries before it passes this. But for something like a symbolic execution engine, this is as simple as issuing a fork and knowing that bad food is this way and not bad food is the other way. However, there's different constructions, like this one, where you're comparing the hashes of 2 D words, let's say. And this is going to be really, really hard for that same symbolic execution engine, because it's going to get a path explosion problem when it's trying to calculate this hash function, and then again when it's trying to compare it to the other hash function. However, this is going to be pretty easy for even a stupid naive fuzzer, because eventually, probably relatively quickly, depending on your strategy, you're just going to generate 2 D words that are the same, probably 2 D words of 0. And so you'll get past this if statement really, really quickly. And so we were thinking about this, and we were like, well, there's these kinds of tools, what can we do with them? And we had a realization. So all of the under-approximate analysis tools are operating over the same domain, which is the domain of the program that you are analyzing. Since these tools under-approximate, anything they find is going to be true for every single other tool, because they're all operating over the same domain, and they don't make any assumptions that aren't true for some concrete execution of the program. And so what if these tools could share discoveries with each other? And that's when we came up with the concept of analysis boosting. And so by sharing discoveries across tools, we can create a virtuous cycle between each tool set that removes roadblocks and create a single better analysis from this. And this is actually named for the concept of classifier boosting, if any of you guys are familiar with machine learning, where you have 2 weak learners and you combine them together to make a stronger learner. In this case, we have 2 relatively weak analyses, and we can combine them together to create a single, strictly stronger analysis. There's one that is going to find more bugs than either of the 2 could by themselves. And we're going to demonstrate this with this code snippet. to where, let's say, you have these two different conditions guarding a possible buggy placed in your program. So neither the symbolic execution nor the fuzzing engine could find this bug on its own, but working together they could, since the symbolic execution engine could identify that, hey, I know a path with new code after you have bad food as the first D word, and it'll get past the first blocking if statement, and then if it could pass its knowledge onto a fuzzer or some other tool, it could then brute force until it got past the second input. And each tool would be removing the roadblock for the other tool, and both of them working together will get you a bug. And so, this was some pretty good theory, but we're like, well, we have 6 months to go, and theory isn't going to find us bugs. So how do we combine some existing tools and get some leverage out of this method? Because we need results soon. And then we were thinking about this, and then realized that there is kind of a universal knowledge that's already shared, or at least kind of shared amongst various tools, that's relatively easy to clobber together and make things cooperate. And that knowledge is program inputs. And so, using program inputs that are consumed by existing tools and emitted by existing tools, we could create one omni tool that would essentially create a virtuous cycle between all of the subcomponents. And so the way this would work is, you start with some corpus of inputs, which is for CGC we were given inputs to some binaries, but for other ones this is going to be the blank input set. Then you give this input to various analyses that operate on something given a program input. And these analyses are going to then generate new candidate inputs that they know something that reflect something they know about the program. And luckily, most tools that are already working on things like binaries already generate you new inputs, such as crashing inputs, for instance. And finally, the stuff that you have, the new inputs that you generated, have to get merged back into the original input set to create this virtuous cycle and feedback loop. And at the end, you get a whole that is more than the sum of its parts. And so the tricky part here is, how do you merge together the output of these tools back into the input set? So this is actually not as simple of a problem as it seems, because different inputs have different quality. Some inputs are good and some inputs are not. So this doesn't theoretically affect the performance of it, but in practice, this really matters that you remove the bad inputs from your input corpus. And the way we ended up resolving this is something that we call the min set. And the min set is the minimum set of maximal code coverage inputs. And so every time some tool generates a new potential input, and something like a fuzzer will, or especially a naive fuzzer, will generate tons of these in a hurry, it goes back to our input corpus, and the min set determines if this particular input gains new branch coverage over the inputs that are there already. And if it does, it gets added to the input corpus and seeded to all the other tools as a new starting input, so they can bypass whatever roadblocks are blocking them. And so that's how we end up filtering out the things we don't want and keeping the things we do. And an analogy for this that I like to use is that the tools that we combine ends up being kind of like the Triforce. So each piece of the Triforce has its own powers and finds several kinds of bugs. But when you combine them together as the min set, using the min set, we form a single entity that gives us a strictly better analysis. And this actually works. So here we have a real crash history track of one of the binaries that we ended up testing this on. And you can see that it goes to one tool, which is a symbolic execution engine, and it goes to a different symbolic execution engine. And finally, after those bypass some roadblocks, it'll go to a fuzzer that actually triggers the crashing condition. And now, I'm going to talk a little more about these separate pieces of the Triforce. Each one of these is kind of cool in itself. We'll talk about the enhancements we made to fuzzing and symbolic execution. So first of all, I'm going to talk about GER, which is our faster fuzzer. So fuzzing is slow. And whenever I say this, normally people don't believe me because they're like, fuzzing is the fastest thing we've got. What are you talking about? But it's actually not true. And I'm going to show you why fuzzing, as currently usually done, is actually very slow. So first, you have mutation delay. And this is a delay that you go from getting some kind of input to getting it mutated, be it the null set or be it an existing input. And this can be super quick if you're flipping bits, or it can take a while if you have some complex markup chain or generation algorithm. Then you have instrumentation overhead. And instrumentation overhead can be huge. And so this is either anything from like waiting for your operating system to dump a core file, to like overhead of a debug API like ptrace and its inter-process communication, or it can be something complex like starting up a whole new QEMU instance and emulating a whole computer system just to get at the memory of a single process. And like that takes a while. Next, there's startup delay. So any kind of program that you're going to run, like the first thing it's going to do is not read your input and feed it like an interesting function that processes it. Like it's going to parse some configuration files, it's going to allocate memory, it's going to print a really long, welcome to my server string. Like it's not going to be reading your input first thing. And finally, there's kernel overhead. And this is the overhead it takes for you to call a kernel system call, for the system call to process and then return. And this might not sound like much, but when you have a box with, let's say, 100 fuzzer processes all taking up max CPU, this is really going to get significant because you're context switching all the time when you could be executing. And so we decided to build GR because there was simply too much latency in the fuzzing process for what we were doing and for the features that we needed to have. And so the problem was that we saw that most of the time that something is fuzzing, you're actually waiting for input. Like you're not actually doing anything for most of the fuzzing process. You're just simply waiting to get to the part where you shove input into the program and it does something fun with it. And so with GR, we aim to minimize this latency. And our secret to minimizing this latency is dynamic binary translation. And so using DBT, what we could do is, for one, we could save and load snapshots. So you could translate a program, you could execute it, then you could snapshot it at its first point of gathering user input, and then you could reload the snapshot at that point, bypassing this ridiculous startup delay. What else we could do is we could emulate system calls. And since we could emulate system calls, we don't need to call into the kernel. So our fuzzer was entirely CPU bound. And so we could run a lot of these and not really worry about stuff. Also, since we use DBT, we have inline code coverage and inline crash detection. And so we could identify exactly which EAP had a given crashing instruction, which was the invalid memory access, and we knew the exact program path that it used to get there. And as a bonus, we could reuse this infrastructure for code coverage measurements. And since we emulate system calls, you could mutate either on a whole file basis, which has some great information. You could find potentially mutate whole file semantics, or you can mutate on a per system call basis, which is especially useful if, let's say, you're loading from some snapshot deep into processing. And since our mutation and our instrumentation was separate, we could replug different mutation engines and different mutation strategies. And for the CGC, they ended up using Rodamza, which is an existing fuzzer/mutator. And so for what GR has, it ended up being extremely fast. So this is a slightly hard to read graph. It has the execution times of 10,000 input mutations for effectively just Rodamza, then Rodamza plus GR, and then compares the same thing to pin. And so having, so executing GR with like branch coverage and crash detection and snapshot loading and everything else, we're about 3 times as slow as native execution, but about twice as fast as pin. And this is before we actually started making any GR optimizations. And so that's it for fuzzer, and next I'm going to move on to one of our 2 symbolic execution engines. So the next piece of our Triforce is something we call PSE. And PSE is based on an open source project called PySymEmu, and PSE is a Python-based symbolic execution engine. And we saw the open source project, and we thought it was fantastic, so we hired its author. And PSE works by directly translating x86 binary code into symbolic expressions. And so it has like essentially like a fetch, decode, add symbolic expression loop. And the great thing about it is that it supports self-modifying code, which is fairly rare for a symbolic execution platform. And the reason that we really needed this is because we thought that there was going to be a serious chance that the qualifier event was going to have self-modifying code. Additionally, PSE supports pluggable CPU and OS models. So all we had to do was effectively write a system call model for to create the CGC operating system, plug it into the x86 32-bit CPU model, and you could immediately begin working on stuff. Also, a lot of symbolic execution engines are limited by how much RAM they consume. To get around this and sacrificing some execution speed, what PSE does is it saves states to disk. And then you can have a pluggable next state search strategy. And so with this, we're actually able to explore more of the program state, but sacrificing the speed at which we explore it. And so to make PSE work with our MinSet and our Triforce, we added 2 enhancements to it. So one is we could start with an initial concrete input. And so we could specify, like, here's the input you're starting with, and every time you get to the input system call, like, read these concrete bytes and shove it in there instead of using symbolic data. And this could, number one, work with MinSet, number two, help avoid the path explosion problem. And the other thing we did is that we made PSC work with initial GER snapshots. So remember when I said before that our fuzzer could take snapshots of programs effectively any time during execution? So what we could do is we could be executing a program, take a snapshot, and then feed it to our symbolic execution engine, which would load CPU and memory state with the contents of that snapshot, also helping bypass annoying path explosion issues. The next symbolic execution we used was CLE. And CLE is a well-known symbolic execution engine that operates on LLVM bitcode. And for those of you who don't know, LLVM bitcode is like a typed assembly language in static single assignment form, usually emitted by the Clang C compiler. And whenever I say we use CLE, people are like, wait a minute, I thought CLE only works with things with source code. And that's not quite true, because CLE only works with things with LLVM. And at Trail of Bits, we developed a tool to translate binaries to LLVM bitcode. This is actually open source, by the way, if you want to download it. It's on our GitHub. And what we could do is we could take a CGC binary, translate it to LLVM with Mixema, our translator, and then execute it with CLE and see if it found any bugs. And like the most amazing part was like this actually worked. We weren't sure this would, but it did. And it actually finds some bugs that the other 2 methods did not. And so we kept it in there because adding new tools doesn't hurt us. It can only help us bypass more roadblocks. It doesn't work on everything. There's like a whole lot of host of issues, such as CLE support for like non-power of 2-bit widths, and like there's memory model differences that make this fail in some instances. But sometimes it worked, and when it worked, it was useful. And so we had some bug finding down, and we were like, okay, like we got something. We're like, the bugs are being found. Let's progress. And then we had the second scored event, and the second scored event was held in April 2015. So this means there's about 2 months to go before the final. And we got ready for this, and we were excited. We were a lot more hopeful than last time. And we went into the second scored event, and our score was 0. And so once again, a lot of the time was spent getting the system up and running. It took not as much time as the first time. We had improved. And we realized that we'd spent all this time finding bugs, and we'd spent all this time like getting this infrastructure working, that we neglected to do the part that like does the scoring, which is patching bugs. And so what do you mean by patching bugs? So patching bugs means making the binary not crash. And so you can do it one of 2 ways. Number one is you can fix the actual underlying issue, or number 2, you can just detect that you're going to crash and exit 0. And you kind of ended up doing the second method. So the other thing I'd like to say about patching is that patching is for white hats, and this is a conference focused on offense. So I'm not going to dwell too much longer on this, but we did a lot of really cool stuff. Like for instance, like we could patch bugs we didn't know about, and we patch at the LLVM level. But you can talk to me afterwards if you want to hear more about our awesome patching methods. And I just did include this slide here. This is our development time. This is time spent patching and time spent not patching. But during the brief patching moment, like it was like a Rocky montage of like doing cool shit and like training against our opponent. Because like we started like at a really bad place, and like we were like learning compiler kung fu, and we were doing all these crazy compiler optimizations like cross-block dead store elimination. We were like doing dominator tree traversal and like various pruning, and like it got nuts. And at the end, like we were patching stuff, and like we were patching stuff, and the stuff we were patching, the bugs were eliminated, and it ran like good enough, and we were excited for it. And so like in like the last 2 months, like things finally got together. So our distributed system worked. And when it worked, it was awesome, because you could type one command line, and it would go and it would create nodes in Amazon EC2. It would automatically provision them with the latest stuff we had in Git. It would run self-tests. We'd give it some binaries, and it would run those through the system, and it'd tell us what score we had. And like, you finally like have like a spreadsheet where you could do like nightly tests, and we could like improve our bug finding count. And so like we finally got there. We could patch, we could find bugs. The patching performance seemed okay, and like we were web scale. Like, we tested scaling this out to hundreds of Amazon nodes and like thousands of cores. And so the final test was in June 2015. And like we had worked really hard for a year to get to this point. And what was ahead of us was 24 hours of head-to-head competition of computer versus computer. It's like once we ran this thing, there was going to be no human intervention allowed. And so we really wanted to make sure that like we didn't have any stupid failures. So we went all out. We ran our system on Amazon EC2, as I've already mentioned. And we ended up using about 300 C4.8x large Amazon EC2 instances. This is effectively almost all of their United States capacity for this. Running at about 10,000 cores with 18 terabytes of RAM and across 3 EC2 availability zones. And it took 2.5 hours on the phone with Amazon to like set all this stuff up. And so this, I told you I'd have another Amazon story. So I'm setting this up the midnight before the actual event. And like, I put in a request, I'm like, yeah, give me, 10,000 cores. And like, it says like, no, we have to wait for authorization. I'm like, oh, I must have triggered some fraud alert. So I call up Amazon, and like, I reach a guy in Sydney, Australia, because their US support isn't working right now. And I'm like, yeah, like, I need this ridiculously large amount of EC2 instances. The guy, like, he didn't like ask me what it was doing, and he was like, okay, I'm going to help you get these. And me and him were on together on the phone, brute forcing like their limits that they could do without authorization. Like we were binary searching through the ones he was unblocking my account, and I try a new one to see how much we could get away with. And he was on the phone with the data centers in the US, and he was going to be like, okay, it's like, this EC2 region has this many, 24 nodes for you. Like, create 24 nodes there. And I could do that since we had all of our DevOps stuff scripted up. So I could type a command line, say 24 nodes here, add them for, this name Cyberdyne instance, and like it would work. And so like finally, like all the DevOps stuff paid off. Like we could do this. And in this manner, we set up about 300 of these. And so whenever I have this slide on, people are like, so how much did this cost? And we spent about $27,000 within 24 hours on Amazon EC2. But it didn't have to cost this much. We were really, really paranoid. So we actually ran 3 independent instances of Cyberdyne, each one in a different availability region, because we were really terrified that there was going to be some kind of region-wide EC2 outage, and we'd spend all this year working towards it, and we were just going to be undone by Amazon. And we didn't know how many binaries we were going to get. DARPA just promised at least 100, which could be anything. It could be thousands. And it turned out to be 131. So we way, way over-provisioned by about a factor of 15x. And to get the same result that we got, like assuming normal conditions, we could have spent about 1.8K or maybe less if had we chosen to optimize stuff. So during this, during the CQ, like everything worked. Like our DevOps stuff ran, like we were finding bugs, and like we had self-estimated score, and so it would say like, found this many bugs, this is our, we patched it, like this is our estimated performance score. And like we thought we were kicking ass, like we were live tweeting this, I'm sure you can still find the tweet somewhere. And so we were doing really well. By self-estimation, we had around 100 points, and the top 7 qualified. And they're like, okay, we might not have gotten number 1, maybe 4 else secure still beat us, but we're like, we probably got like 2 or maybe 3. And then 4 weeks later, we got the phone call, and we got 9th. And this was like super devastating for us, because we had worked so hard all year, and especially at the end, and like we thought we had done really well, and we're like, so what happened? Like we really couldn't believe it for a while, but eventually the data set was released, and we could actually do a post-mortem of how we did. And so, start with the good news. The good news is, in terms of finding bugs, we were number 2. Out of all the teams there, like we started from nothing, and we ended up making something that was not quite as good, but kind of as good as getting close to mayhem in terms of bug findability with 4 remote people. And so we were super proud of that. They're like, okay, #2 in bugs found. In terms of patching, effectiveness, we were number 5. And so we were 5th in terms of the amount of binaries where we were able to remove the bug and essentially make the binary not crash with the original crashing input. But in terms of performance of our patched binaries, we were last. And we weren't just last, but we were dead last. And it turns out that the self-measurement performance metrics we have were simply wrong. And so the rules about it were pretty clear. We read them up front, and we had 2 times where we could have measured how well we did performance-wise. So the actual metrics were hidden for good reason, because people knew the exact metrics and they could game the system. So the metrics were hidden for a very good reason. And so we had to self-estimate, and our self-estimates were completely off. And we ended up focusing on doing the wrong stuff, and we honestly picked to do stuff in the wrong order. There's plenty of things we could have done to make it different. So we sadly failed, but others go on. CGC isn't over. I encourage everybody here to go to the CGC final event. It's co-located with DEF CON. It's free and it's open to the public. However, things were not done for us. So we were like, you can't patch stuff, but we have this automated bug finding system that finds bugs that's pretty good. What are we going to do with it? And so we're like, yeah, let's go find some Linux bugs. So we couldn't really do this directly, because this was written for a different simplified operating system. And this operating system called the Creep didn't have a file system. It didn't have users, it didn't have environment variables. You kind of need all those things to fuzz Linux stuff. And so we created a LLVM-based wrapper that emulated all of this. And so we built everything to one giant LLVM blob, and then we optimized that blob, and then we ended up creating a decree-based bundle from a Linux library and a little driver to extract the functionality. And so our first test was for charity. There was a bet between Tom Kachek and Matt Green about finding bugs in libOTR. And we were like, okay, this seems like a good test case. Let's see if we can find any bugs in this. And we did, but we weren't discouraged. Number 1, because we kept authentication codes and encryption on, so we were only really going after stuff pre-encryption. We weren't really going to be seeing stuff post-encryption. And we showed that our tool set for taking a Linux stuff and making a decree binary out of it was okay. Next, we moved on to a different target. So the hardest part of doing the libOTR test was building the stupid driver to actually invoke the functionality and test stuff. And so we went on GitHub and we looked for stuff with a built-in fuzzing driver, and we found libharfuzz as the first or second result, since they use liblvmfuzz for internal testing. And we were like, okay, cool, this is a C++-based font shaping library. This thing has to be full of bugs. This is going to be an amazing test. And we could do this so we could see if we could handle C++. Since previously we'd only done C. And so we did the stuff and we ran it for a day, and we were like, this is really odd, we're not finding anything. And so then we looked at the commit logs and we were like, oh, Google already fuzzed it. They have a fuzzing bot that already goes after this thing and found all of the reachable bugs. And so we went back, reverted a few commit versions, and ran it on the untested one, and sure enough, we could re-find the bugs. And so then we're like, oh, all right, this is getting better. We know that we can find legit bugs and stuff, real programs. And so then we went on to a slightly softer target. We were like, okay, Apple also has an open source thing, and their code is probably lower quality, and Google hasn't been fuzzing it. And we were like, let's test the Apple version of libarchive. And I would like to irresponsibly disclose that there are several crashes in libarchive that are very easily reachable, and these work on OS X current. This is one of them. The other one wouldn't fit on the slide. There's probably more. Go find them. And so in libarchive, this thing worked, and this is just an untar. The other ones probably have a lot more. And originally, we picked libarchive because we wanted to do a comparison against AFL. So Andrew was running AFL and libarchive for a different thing, and we couldn't end up not being able to do that comparison simply because it ended up being kind of apples to oranges, simply because of time and CPU requirements. But we still have the obligatory comparison to AFL slide. And so the gray bars that you see, the first three are different tools, clean, PSC, and GUR, running independently on the CQE binaries. And you just see how they do. So most of the bugs are found by fuzzing. And then you see a union of them. And the union of them is how each of the, like if you combine all the crashes into one big set, how well they did without helping each other. And then the boosted one is how well you do when you do analysis boosting and combine those exact same tools via MinSet. And we see that you could find 4 additional bugs, despite the fact that now all of these were co-located on the same machines, so each one actually had proportionally less resources to do the actual bug finding. Even though they had less resources, they were still better when they could help each other eliminate roadblocks. And finally, the team from UC Santa Barbara published a paper called Driller, where they ran AFL, like using a QEMU backend on the actual binaries, and they were able to find crashes in 68 of the binaries. I'd like to note that they probably did not actually use this for their qualifying event, or they would have done better. So this has been done afterwards. But I really didn't want to have this slide originally because it makes it seem that like, hey, like you guys put in all that effort and you found like one AFL. It's like, what are you guys thinking? But like that's not the point. The point is that we don't have to pick whether we're going to use AFL or all of this other stuff. The point is that we could use both. You don't have to choose. The analysis boosting architecture is designed in such a way that we could plug AFL, or like a whole AFL farm into this, since it takes inputs in and emits new paths, which are outputs. So we could use AFL with this. And so that's what I want to do in my conclusion slide. So we have been building bug finding tools wrong. Right now, there's 2 different ways that bug finding tools are built. One of these is like gigantic systems that take a whole team of PhD students to assemble, and once they all graduate, nobody can figure out how to use them anymore. The other ones are like small standalone tools that find a certain class of bugs. And these are great, and these are on production code, but they're not as good as they could be. But what we should be doing is developing small cooperative tools that work together. And especially this is going to be true when you have to start distributing things. And so I'd like to have my concluding slides with an analogy. So the stuff you're building right now is like a Cray 1. And a Cray 1 was an amazing supercomputer when it was developed. And it was large and integrated with custom everything, like custom CPU, custom interconnects, custom ICs, custom cooling. And fairly quickly, the Cray 1 ended up being in a museum as a footrest because you couldn't really repair or maintain it, and everything was super expensive. And once the knowledge was lost, now people are even trying to figure out how to preserve this and run it in an emulator because nobody knows. But this is the Cray Titan. And the Cray Titan is made by the same company as the Cray 1. And it's the #2 supercomputer in the world right now. However, the Cray Titan is fundamentally different because it's built of off-the-shelf parts connected together using smart custom interconnects. And the Cray Titan is going to be useful for years because as budgets change or you need more performance, you can simply add more nodes. And you can repair and replace it, and like other people can write stuff that actually runs on it. And so what we should be doing is we should be building things that are more like the Cray Titan, off-the-shelf components that can communicate together and achieve a result. And for the final slide, I'm going to tell you how to unleash the power within your tools by making them communicate together with a great motivator named Tony Robbins. And I mean, if Tony Robbins can't motivate you to do something, I don't know who else can. And so unleash the power within your bug finding tools. Publish your machine state, like make it so that other people can work with your tool and talk with it, and then you can use other people's tools to gain better understandings of programs. Like, you don't have to agree on a standard now. Like, as long as everybody does something, you can figure out how all these things interconnect at the end. So please, when you're making bug finding tools, make your data accessible, and that way we can all find more bugs and win. Thank you.